Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. Section 3.1 of the Configuration Spaces chapter. Problem Setup, Multibody Robots in Realistic Workspaces. Recall that we have worked so far with a planar workspace, W, which is a subset of R2, some obstacles that we've labeled O1 through ON, and a point robot with no shape, size, or orientation. We then defined the free workspace, W free, to be the workspace set minus, the union of the obstacles, as the set of locations where a point robot is not hitting any obstacle. A feasible motion plan for a point robot is computed as a path in W free. In this chapter, we begin to consider robots that are more realistic than the point robot by considering robots with a finite shape or size. As illustrated in Figure 3.1, path planning algorithms for point robots are not immediately applicable to robots with a shape. So we see in A, this point robot able to move right between obstacles 1 and 2 with no problem, whereas in B, we would have a collision because the robot has some size that won't fit between these two obstacles. So we can't just treat a robot as a point and use the preceding methods that assume the robot as a point, but we can use them and then extend them to include the robot with some finite size. Okay, we start with some simple concepts. 1, a rigid body is a collection of particles whose position relative to one another is fixed. A robot is composed of a single rigid body or multiple interconnected rigid bodies. 3, robots are three-dimensional in nature, but this chapter focuses on planar problems. We postpone three-dimensional rigid bodies to the later chapters on kinematics. Note, we do not consider flexible or deformable shapes. As in general, an infinite number of variables is required to represent such robots. Example systems. Let us discuss a few preliminary examples of more complex robots. We consider only planar systems composed of either a single rigid body or multiple interconnected rigid bodies. The first one is given here, with the robot being a circle and with translation in two directions allowed for the robot and these two triangular obstacles. The disk robot has the shape of a disk and is characterized by just one parameter, its radius, r greater than 0. The disk robot does not have an orientation. Accordingly, the disk robot's only motion is translation in the plane, that is, translations in the horizontal and vertical directions. Here's our second robot in a workspace. The translating polygon robot, or translating planar robot, has a polygonal shape. For example, a ship-like shape in the side figure. So here's a ship-like shape. This robot is assumed to have a fixed orientation, and thus its only motion is translations in the plane. So we have a fixed orientation, we can translate but not rotate here. Okay, here's another example. We have the roto-translating polygon robot with an arbitrary polygonal shape. It's capable of translating in the horizontal and vertical directions as well as rotating. So we can translate and also rotate orientation. Okay, finally, we have a multi-link or multi-body robot that is composed of multiple rigid bodies or links that are interconnected. Each link of the robot can rotate and translate in the plane, but these motions are constrained by connections to the other links and to the robot base. The one-link robot is described by just a single angle, so this is the one-link robot. The two-link robot, this one here, is described by two angles, the angle of the first link and the angle of the second link. Multibody robots are commonly used in industrial manipulation tasks. An example of an industrial manipulator 3.2 below. right here. Robots with higher numbers of degrees of freedom are also of interest. For example, see figure 3.3, where we have this higher degree of freedom robot. So that is all for this problem setup section, and I'll see you next time.